My mission is involving 3D printing on Mars. Named it Regobot, just for the regolith. So we'll start with the mission concept and objectives. But before we get to that, I just want to talk a little bit about the inspiration for this mission and the, I guess, theory behind it. Starting off with just saying that Mars is an extremely important celestial body overall, not only because it will prove that humans are an interplanetary species, but because it can be used as a stepping stone to achieve even greater goals and do more research farther out in the solar system. The whole concept of humans on Mars is especially talked about recently with Elon Musk, exciting. But a lot of the current media focuses on what human colonies would look like with humans actually there, or what kind of spaceships will get them there. While those two things are extremely important, there's one crucial step in between, and that's making sure that humans arrive at a place that's ready for them, that's already prepared with some substantial amount of infrastructure. Right now, a major issue for humans on Mars would be radiation and shelter from various weather events and the atmosphere, things like that. The best way to protect astronauts from these things is definitely a habitat, but in a lot of different sci-fi movies and concepts now, they're kind of either inflatable habitats or they're brought on the same mission as the humans. That wouldn't really be sustainable or efficient in any sort of way. A different thing that people could work on is bringing a robot, semi-autonomous robot, before, maybe years or even decades before humans ever get to the planet, and then 3D printing these habitats. This is where my mission concept comes in. 3D printing small habitats, storage modules for things like air and rocket fuel. And then all of the materials for 3D printing would be sustainably collected from the Martian surface, and then mixed and then printed from the rover using a multi-directional arm to print out constantly changed files that would be uploaded from Earth. A secondary mission goal would be to collect more data on the Martian surface over a much wider area. This is definitely possible because cement and concrete printing technology already exists on Earth. It's been quite a bit in the media recently, actually. And the materials needed for it are relatively simple and definitely abundant on the Martian surface. So things like aluminum, silicon, iron, sand, water can be found in ice, in the crust. Everything is already there. Here's a science traceability matrix that I've constructed, with the primary goal being to manipulate non-Earth environments with remotely controlled autonomous machines in situ, further utilizing space resources, so things that have already been on the planet and not really brought with you. Some science objectives would be to demonstrate that habitation for the human race can be constructed using materials that are already found on extraterrestrial bodies, and then to confirm that autonomous solar-powered machines can build the above-mentioned habitation using plans uploaded from Earth. Some observables for measuring these scientific objectives and goals would be to test the building with increasingly heavier loads, do a time lapse of the building and maybe erosion of the building with an outside camera, and then using air pressure gauges, radiation testing equipment, thermometers, things like that, just inside the actual building itself on completion. Some mission requirements at the top level that need to get done is at least a 1-year lifespan. It would hypothetically be fully solar powered, and then build a minimum of 3 different habitat designs. Of course, it would collect all the building materials from Mars and then perform outside mapping of the Martian region to optimize the collection site and further data. And then a pretty cool idea is that the rover would take shelter in the completed habitat during dust storms, just to kind of avoid that whole catastrophe of the rover getting covered in sand and stuff like that and then not being able to move. After looking at your guys' past projects and backgrounds and things like that, I thought including a mission cost projection would be pretty interesting. So using this chart, the way that I went about this is looking at the various missions that have been done before that are pretty similar in concept, and then using that cost and kind of comparing it. So the one that I thought was pretty similar is the Perseverance Mars mission, with a projected cost of 2.7 billion US dollars, but an actual cost of 2.9. And this mission is still operational, you know, just landed this year. Mission duration fees are still being added, so the cost is going up. My concept would be pretty similar, but have a few different things, bringing the cost up to around 4 billion. With a similar style launch, mission structure, and then rover, but an extremely different purpose, technology, and lifespan. It would intentionally operate as long as possible instead of kind of completing the mission and then just stopping. While it would be majorly autonomous, consistent ground control would be needed, especially at the early phases of the mission. And that would be for continuous updating of the software, maybe hardware, and structural blueprints. And then some HAB design modifications could be necessary based on new findings. Maybe the region has changed. And then the space program that's running this mission would need to contract outside builders or architects if necessary, which would also provide an ongoing cost for the mission duration. I've listed some of the mission cost deviators that might be possible, such as the extended prototyping or the R&D phase, which would increase the overall cost through the cost of materials and time spent. If the landing zone is well suited and mapped out relatively quickly, then ground control time would go down, bringing the overall mission cost down. If the timing of the TRL requirements is off, then the launch window would be missed. Maybe the time spent before launch, paying a bunch of things would increase the overall mission cost. And then, of course, if the blueprints for the habitats need to be modified, then outside or internal design help is brought in, and that would increase the overall mission cost. I just want to quickly go over some mission instrumentation that would be necessary. So the main piece of technology on this mission would be the printer. So 3D printers and fabricators already exist on the ISS. Obviously, cement ones don't. But yeah, cement ones have never really been tested in space either, and certainly never tested in the kind of collaboration with a rover mission, even on Earth. So that would be one of the biggest pieces of technology that could maybe present a setback. In terms of the rest of the things, sensors like spectrometers, tensiometers, maybe external cameras, sensors to determine the ability to sustain life like barometers, thermometers, a camera, things like that are already on rovers. So that wouldn't really present too much of a challenge handling new technology. Just need to make sure that works. And then we could add a small stationary camera kind of on its own stand to time-lapse the weather and build process. And then an orbiter and lander is necessary to observe the best possible place to land and then begin construction and soil analysis. And then solar panels and power is already being used on rovers, and a file upload system from Earth is already being used on rovers. We can quickly go over this block diagram of what the mission timeline would look like overall. The aqua boxes represent the overall mission requirements, red is for construction, and then green is for science. So it would start out with the landing of the rover, do some system diagnostics, and then the rover would leave the lander and scout out the surrounding area, making a terrain and soil analysis map. Then the rover would send the map and the data back to Earth, and then the ground station would kind of decide where the best location is and which specific set of blueprints for that location would be the most optimal. The rover would then spend some time collecting materials and then 3D print the habitat over the span of a few months. Remember, just because humans aren't there yet, it would be maybe decades before humans ever get there. Time is not really that much of a constraint, so it can spend as much time making sure that it gets the finer details correct, making sure that it's as safe as possible. The rover would then take shelter in the habitat during dust storms, goes maybe into hibernation mode or something, then go out and recharge the batteries, receive blueprints for future habitats, and then would just repeat this cycle until humans get to Mars. So we can now look at this simulated mission in Kerbal Space Program that I made. I can full screen it here. The main concept that I wanted to focus on with this simulation is the payload, which I also constructed beforehand. And that's, I think, the biggest consideration for me, just because, you know, obviously launches like this to Mars with rovers have been done many times before, but this specific payload, the size of it with the Skycrane and everything like that hasn't really been done before. So that would be a consideration to look at. So this simulation starts launching, fairing deployment, first stage detaches, and then the second stage goes into a stable orbit around the Earth analog. And then I get into one of the more complicated aspects of this simulation, which is making sure that the intercept between the rocket and Mars is correct. As in real life in the simulation, there's a specific launch window that you need to meet to make sure that you get a good intercept. And then just to reduce the launch mess as much as possible, I didn't want to carry any sort of extra fuel. So making sure that I got it pretty much perfect and accurate is pretty necessary. So there was the second stage detachment there, a few in-course adjustments, and then we arrive outside of Mars with the third stage detachment, and then the inflation of a heat shield, the only one in the game big enough for this payload. Pretty nice animation. And then we are going to be entering the Martian atmosphere relatively soon. And this is where the simulation, we start to see some limitations of this program. Yeah, the entry was not as perfect as I'd hoped it would be. It kind of started spinning around and everything. It just didn't work out. But I found a way around it and then kind of just cut to the descent itself. After stabilizing, you can see we're using the parachutes for a nice soft landing all the way down. I extend a secondary antenna for better communication with Earth. And then we'll use the parachutes quite a ways down and then use the Skycrane in the last stretch, just as in regular actual in-life missions that we've seen recently. So it starts off by detaching the heat shield. I had to include this scene just because there's a very nice explosion at the end of it, as you'll see in 1 second. Very nice. And then I detached the parachutes, and then you can see the Skycrane being put to work here. There is a ridiculous amount of delta V in this specific design for the Skycrane. So yeah, very soft, nice landing. And then the Skycrane itself will detach and fly away, as was demonstrated in the latest Perseverance launch and landing. The Skycrane detaches and then shoots off until it runs out of fuel, and then will crash somewhere else on the planet. And then we can come back to the rover and start messing around with the actual instrumentation that I've put on here. So the in-game science and engineering is pretty limited on rovers themselves, but I did manage to find a few analogs that could be used here, such as these drills are pretty representative of what a hypothetical collection system would look like for this rover. Obviously not perfectly correct, but pretty close to the actual size. And then here I start deploying the external camera, turning it on and stuff. Inside the actual rover is a material refinement center and then a kind of bay that opens with the robotic arm inside. Unfortunately, it is not able to be shown here. But yes, that's the main body of the rover. And then I think that's pretty much this mission is complete in the simulation here. And yeah, it was a success. So if anyone has any questions or anything, now is a good time.
Great job, Kurt. Really great. I think the boys sometimes even undersell how much they do by hand within the program, because they have 10 to 15 minutes, which both of you were within time. Excellent.
Very nice.
But even I know that Kurt, you had to even construct the Skycrane within Kerbal Space Program. That wasn't like a pre-made part, right?
Yeah, actually, none of the payload or the launcher itself was pre-made. I tried to model it as much as possible.
Exactly. Yeah, I just wanted to point that out. All right. So yes, James, Guillaume, questions for
Guillaume, you want to go first this time?
Yeah. So once again, that was really cool. I think maybe for proof of mission, having something like a Kerbal Space Program is actually really helpful to understand the whole process. So it's not my specialty. So on the science part, I'm not gonna be as pertinent as Mel or James. But I can ask you, I think, a question which is a little bit tricky, but I think someone from a space agency will ask that, like seeing this kind of concept, particularly in this time, it will be, why choosing Mars over the moon for like to test some habitats?
Right, definitely. So moon habitats have been, I mean, I've seen a bunch of different sci-fi concepts of it before, and they're definitely the first stepping stone to some sort of habitat construction and everything like that. But the eventual plan that's being constructed right now is to have humans on Mars. And if I was going to go through this whole, I don't know, process of getting all the scientific data and analysis and everything like that, just really constructing this mission, I thought it would be, I guess, more prudent to go all the way to the final destination rather than a bit less of a proof of concept for the technology on a different planet, I guess, or a different body.
Yeah, in a way also, I think like I will feel that right now everyone is looking at the moon. So if you like project something on Mars, you will surprise some people, like, or you will like, I will say, take a little advantage to some other like nations. Like I'm thinking about China, for example.
Right. Yeah.
So yeah, and I think what actually make it work in like what it make it like kind of like reassuring for accountants people, I will say, is like it's not only about like building something. There's also this analysis part at the beginning
Mm.
that will like ease up a little bit the bill, definitely.
Yeah, definitely.
Yeah, so why would the moon be useful?
Just in terms of constructing habitation, you mean? Or
Yeah, so you went directly to Mars because you felt like it would be better to go straight to the end point. But if you were going to go to the moon, why? What advantages would that have over going straight to Mars?
oh, definitely. Well, there's the obvious advantage of being a lot closer, so more missions can be sent in a relatively short time period. You know, there's no 7-month launch window or whatever, 2 years that we have to wait every time. And then yeah. And then one consideration is the material. We know significantly more, I think, about the material on the moon. Yeah.
Yeah, so this is why people have turned focus to the moon recently, is because it is closer and it's your bill would go down for the same mission. Because you need a much smaller launcher to get it there. You don't have the entry, descent, and landing phase problems that you have with Mars. And the idea is basically you can still learn quite a bit that then you would translate over to your more expensive in Mars. But I think, yeah, there's something to be said for going straight to Mars also because, yeah, the soils are different and everything is different. So, yeah.
Yeah, definitely.
Another question I had was about, one of the challenges with 3D printing, at least with extrusion printing, is that it's not like the prints aren't watertight. For example, they don't hold
Right.
air very well. You're trying to build a habitat in a low pressure environment, and then you need people to have a higher pressure environment inside. How are you going to deal with that?
Right. That is definitely a consideration that needs to be thought about. One possibility is that 3D printing just gets a lot more accurate in the next several years. Machines are evolving every year now. But I think the main consideration for these habitats would that they would be more radiation shielding and kind of storage modules. And then once humans arrive, they could, line the inside with some sort of smaller material or something.
Yeah, like a bubble or something. Yeah.
Right.
Yeah, it's a good idea. In general, I really like the concept, right? Because you get the printer down, and really the question is about how to design the building. And you can just continuously keep trying buildings as long as you want until you have a design that works with the same mission. You can just, right, iterate
Yeah,
on the
exactly.
building design. And that's really kind of the part that we don't know that much about, really. So I think in a lot of ways, it's a kind of cool mission concept because you get a lot of value out of the same machine.
Definitely. Yeah.
Yeah. So those are my questions.